All right, so we're going to talk about something today called the moment of inertia. Okay. The moment of inertia. What does inertia mean? No, the regular definition for inertia. What's it mean? Good. Good. An object in motion stays in motion. An object at rest tends to stay at rest. So when we talk about the moment of inertia, we're talking about basically how much that object will resist coming to motion, right? Well, how much it will resist rotation, right? When an object is at rest, it wants to stay at rest. So the moment of inertia is basically how much is it going to take to get that thing started. Okay, it's called that moment of inertia. All right. There's lots of equations for moment of inertia, but this is the most basic. I'll give you a table with some different equations for moment of inertia, but this is the most basic equation. I equals m times r squared. Based on this equation here, what would the units for moment of inertia be? Kilograms times meters squared. Okay? We just take those two variables, whatever their units are, multiply them together. Okay, kilogram times meters squared. Okay. The reason there's so many different equations for moment of inertia is because it depends on the shape of the object. Okay? They have different equations or different formulas for moment of inertia depending on the shape, depending on how the mass is distributed through that object. Okay, so the distribution of mass in a hula hoop is very different than the distribution of mass in a solid circular plate. Right, does that make sense? The distribution of mass is very different in a hula hoop than it would be in just a plate. Right? They might weigh the exact same thing, but in a hula hoop, where is all of the mass? On the outside, right? In a plate that is solid, that mass is distributed evenly through that. So that makes a difference in how likely that object is to resist change, or to resist that rotational motion. Okay, for objects that have most of their mass distributed at the same point around the axes, so that's like a circle, okay, like a hula hoop or a tire, things like that that have even distribution of mass at an even distance from the axis point, we would use the basic formula, that I equals m times r squared. Okay, for the other ones, I'll pass out the table to you that tells the different equations for different circumstances. If there's extras, I'll come grab them in the back, so just leave them. This table you will get on tests. You don't have to memorize these equations, okay? It tells you what shape it goes with and the equation that goes with it.
Oh, yeah.
Okay, so there's a couple different situations on here that look a little similar, and I want to point them out to you. First of all, our first equation on this table is for what is considered a thin hoop. Okay, a hoop. That means anything that is going to be having its mass distributed along the outside or on the outer rim of that object. So we could be talking even about something like this that has its mass only at the end, right? That would be considered a hoop equation because all of the mass is evenly distributed along the outside of that. And if you put it together, it would look like a hula hoop or whatever it is. Okay? And then the second equation on there is for a solid cylinder. So that means the mass is distributed all throughout that entire shape. If you look down to the last 1, 2, 3, so the fourth and the fifth equations for a rod. Okay, I want you to think about that for a rod. The first of which is when our axis is through the center point. Okay, so if you can imagine, a person twirling a baton, they usually hold it in the center. Okay, so that means that we've got masses on either end. The other equation for a rod is when we hold our our axes through the center point. So now we've only got a mass on one end, and it moves however we need it to as such. Okay, so there's a couple different places that you need to pay attention to where the axis point is, or if it's a solid or a hoop type equation. Okay, let's try one here. I'll kind of draw out what's happening here on our picture. Two masses are hanging on a bar. The masses themselves are 4 meters apart. Okay, the masses themselves are 4 meters apart. The mass on the left has a 5 kilogram mass. The mass on the right has a 7 kilogram mass. Okay, when it says the mass of the rod can be ignored, where does that mean that our mass is going to be distributed? Just on the outside, right? We don't care about the rod itself. We just care about the masses that are on the ends there. Okay, so the mass is going to be distributed on the outside. Calculate the moment of inertia when the rod is rotated around the center axis point. So that means our axis is right here in the center, which means how far are each of these masses from the axis point? 2 meters. So our radius for each of these would be 2 meters. Okay. Since these objects don't have the same mass, we have to solve for the moment of inertia for each of them on their own, and then we can add those two together. Okay, since they don't have equal mass, we got to do them on their own. So what equation could we use to solve for that? The first one, right? The first one. The mass is going to be distributed along the outside. Okay, since they're not of equal masses, we can't use that uniform rod equation because they don't have equal masses. So we have no way to account for the fact that they have different masses. Okay? So we're going to use that first equation, I equals mr squared. Okay, for the 5 kilogram mass, it would be 5 times 2 squared. And for the 7 kilogram mass, it would be 7 times 2 squared. Oops. Okay. Did we understand why we're not using that rod equation there? Yeah, we don't have the same masses, so we have no way to account for that. So here we're looking basically as if it were spinning in a hoop, right? And we had one rod, then we're going to look at the other side, and we'll be able to add those together. Okay? Questions here? A big part of these problems is just picking out the right equation. Okay, find the moment of inertia of the same system if it rotates about an axis that's 0.5 meters to the left of the 5 kilogram mass. So now we're not spinning it from the center, we're spinning it from basically the end of one of those. Okay, so let me redraw kind of what that might look like. So now this is our axis point right here. Okay, so that means that distance is 0.5 meters. How far are these two objects still apart? They're still 4 meters apart. So that means the radius for this 7 kilogram object is what? 4.5. All right, so now we still have to solve these separately because can we visualize? We have an axis here and we've got two masses, so it's kind of two little hoops. Right? Can we see what's happening there? Yes or no? Okay, we've got a center axis and then we've got a mass hanging here. So as it rotates, it's going to make two hoop type motions, right? We have two hula hoops, one inside the other. Okay, so if we solve for the 5 kilogram mass, we want the moment of inertia of the total system. So we want the 5 kilogram mass first. I equals mr squared, which would be 5 times, what's the radius now of the 5 kilogram mass? 0.5. Okay, because it's located 0.5 meters from that center axis. And our 7 kilogram mass, moment of inertia, equals mr squared. And now what's the radius of the 7 kilogram mass? 4.5. So we're going to be able to take Newton's second law, which tells us mass times acceleration, and we're going to be able to insert that or connect that now with the moment of inertia. Okay? By taking torque, by taking moment of inertia, and by taking angular acceleration, we can connect them all together. Your book can do a really good job of mapping this out for you, okay, but I'm not going to do that. This is one I would have on your equation sheet for sure. Because you will get the table of moment of inertia equations, but this one will need to be on the equation sheet. Net torque equals moment of inertia times alpha, angular acceleration. All right, a bicycle wheel has a radius of 38 centimeters and is given an angular acceleration of 2.67. We've got a force. What's the wheel's moment of inertia? All right, so here's his bike tire. It has a radius of 0.38 meters. We apply a force to put that wheel in motion, right? We're trying to push that in motion. Our force has a value of 0.35 newtons. Okay, are these two things perpendicular to one another? Yes. So can we solve for the torque using these two values? Yeah, because our force is already perpendicular. We don't have to break it down. There's nothing that we need to do there besides solve for torque. Okay? So torque equals Fr. Okay, do we understand why our force is being applied right here? Okay, does it really matter where our force is applied? If our force would be applied here, right, our radius still goes this way, those things would still be perpendicular. It makes no difference where our force is being applied. I could apply a force this way too on the wheel. My radius still goes here. It's still a perpendicular. Okay, so it makes no difference where on the edge of the wheel we apply that force. It's going to be perpendicular to the radius no matter what. Okay, so we got a torque of 0.133. Our new equation for finding moment of inertia based on its torque is T equals I times A. Okay, so I'd plug in 0.133 equals moment of inertia times 2.67. Divide that over, and I get a moment of inertia of 0.05. Okay. Example 8:12. All right, I wanted you to open it up so that you could see this example here with the picture given, okay, because it's probably a little better than I could draw it, okay? So a 15 Newton force is applied to a cord wrapped around a pulley. Okay, the mass of the pulley is 4 kilograms. Our force is equal to 15 newtons. Our radius is 33 centimeters, which gives us how many meters? 0.33 meters. Okay, pulleys observed to accelerate uniformly from rest to reach an angular speed of 30 radians per second in a time of 3 seconds. Okay, this is throwing a lot of information at us. Okay, I want to get everything down first, and then we can decide what we need to do from there. So we have a frictional force here of frictional torque, 1.10. And we'll see what that means here in just a little bit. Okay. We want to find the moment of inertia. Okay. So let's start thinking about what equations we could use here to solve for the moment of inertia. Yeah, what do you think?
Well, would we have to get acceleration first?
Yeah, we need to solve for acceleration. We need to solve for alpha.
So could you do delta omega over delta phi?
Good. Okay, we can do delta omega over delta t to find alpha. Okay, let's go ahead and do that. Final minus initial, so we'd go 30 minus 0 over 3, which means alpha is equal to 10 radians per second squared. Okay, that's good. This torque of friction, is that going to be our net torque? No. What does our net torque have to be? Force times radius, okay, good. But it has to be the overall. So isn't our tension force going to give us some torque too to make this thing go? Yeah. Okay, so we need to solve for that, right? We need to be able to solve for that torque by our pull before we can take into account that frictional torque. Okay, are we on the same page here? Okay. So let's start finding the torque that's made by our applied force. Okay, this pull. Okay, torque that's made by our applied or our pull. Okay, so how much force did we use to pull that thing down? 15 newtons. And is it perpendicular to the radius? Go ahead and look at your diagram there. Is the pull that we use, is that perpendicular to the radius? Yeah. Yeah. So 15 newtons times 0.33 gives us the torque that happened when we pulled that thing down, the applied torque. Okay, and what did we get when we solved that? 4.95? Okay, 4.95. Okay, so we've got torque by our applied force, we've got torque by friction. So to find net torque, what would we need to do there? Subtract them, right? I want to take friction out because friction is opposing my motion. So I'm going to take 4.95 and I would subtract out my frictional torque, which means net torque would be 3.85 Newton meters. All right, now how can we go about finding our moment of inertia? What new equation do we have that might incorporate torque and alpha? That's right. Net torque equals inertia times alpha. Okay, that's the reason right here, because it was net torque, that we had to take into account our pull and the friction.